Hi guys. So today I'll be talking about text processing part 2. In part 1 we have discussed about tokenization, stop words, stemming and lemmatization. In part 2 I'll be discussing about these few topics, that's one hot encoding, bag of words, n-grams and TF-IDF. So I'll explain what is the story that I'm trying to make out of all this topics that I'm talking about. So just see this one. So for example, we are building an NLP application. So in order to build it, we need to go through certain steps of text processing, and then the machine is able to understand our natural language. Natural language is basically what we speak, and machine do not understand natural languages. They understand a different language, that's vectors. So first steps comes with that we have this data set. Okay, so this data set goes and we do text processing part one, text pre-processing part one. And in text pre-processing, what we do things like lower casing our corpus of data. Then we do tokenization. Okay, then we move ahead with text processing part two. Here, what we do stemming, lemmatization, stop words removal. All these things we do in part two, text processing part two. Then after all this, then we go to this step where we do word to vectors. That is vector embeddings we try to create to make the machine understand our corpus of data. So there topics comes like bag of words, TF, TF-IDF, one hot encoding, and so on. So today we have already discussed about this parts. Now today we are going to cover this one. That is how we can convert corpus of words to vectors. So before going ahead with this topics, let me just talk about few terminologies that will be consistently working going forward with the topics. Starts with what is corpus. So corpus is basically combination of sentences, and combination of sentences is basically a paragraph. So in NLP language, we call a paragraph or a combination of sentences a corpus of data. Okay. For example, we have these two sentences. We have these two sentences. So these two sentences can combine. We can call it a corpus. Then what is document? So document is basically a sentence. A sentence we call in document in NLP. That is, I'll call this sentence one will be document one. This will be document two. And that is a combination of words that makes up a sentence. We call it a document in NLP. That's terminology two. Now, if we talk about what is vocabulary is basically in a sentence we have multiple words, and all the number of unique words in our document or in our corpus of data is called a vocabulary. So, if I give you an example, for example, if you take example of these two sentences, I am a boy, and in document two it is I am a girl. So, okay, If we try to find out the unique vocabularies, we'll start with I am a boy. And again, I comes, we won't consider it because we have already considered it. We are talking about unique words. So it's a duplicate again. We won't consider this. Not M, not A, and again, girl. So how many unique words or vocabularies we have in this documents? We have I am a boy and girl. That is five, five unique vocabularies. Now, if I talk about words, so words are simple. So it is similar to the words, or you can say it's a token that I'm talking about. Now, if we just move ahead with our topics, so starts with one hot encoding. So what is one hot encoding? So one hot encoding is very simple. That is converting words into vectors, considering word indexes. Okay, what this mean? Let me explain. So for example, just take this particular example. I watch Gaurang-Tech YouTube channel. Okay, this is our document, and after removing of our stopwords, that's I'm considering I as a stopword. So after removing the stopwords, we and doing the tokenization, we get this list. That is this four tokens: watch, Gaurang-Tech, YouTube, and channel. Now, now if we want to represent in one hot encoding, so this is how we do. So when I was talking about considering the word indexes, what I meant was how many words are there. So there are four words, right? So there will be four indexes, as you can see here. There's there are four indexes. So how we are representing it? For a first letter, we'll see where is it present. It is present in the first index. There is one. So the first index will be 1 and the rest will be 0. As you can see, watch can be represented as 1 0 0 0. Similarly, for Gaurang-Tech, for this particular word, it is present in index 2. So in the second index, it will be 1 and the rest will be 0 0 0. So it will be 0 1 0 0. Then again, the third word, that is YouTube. For YouTube, it is present in third index. Then again, in one hot encoding representation, the it will be 1 for the third index and the rest will be 0. So it will be 0 0 1 0. Then for a word channel, it is present at the end. That is in the fourth index. So it will be represented as 0 0 0 1. So as you can see, the total index is basically how many words we have, and we place one in the position where the particular word belongs in the list, and the rest will be uh, named as 0. Okay. Now, if we just talk about the advantages and disadvantages. So again, if I talk about the advantages, it is very simple, intuitive, and easy to understand. As I have already explained, it's very easy. The representation is very easy. But if I talk about the disadvantages, so it creates sparse. So what do you mean by that? So it meaning, for example, just to represent this four words, you can see how many ones and zeros has are required to represent it. So just to explain, just to represent the word watch, we have four ones and zeros. So it creates a lot of memory. It takes up a lot of memory that eventually increases the requirement of computational power and as well as the RAM we require. So that's one disadvantage. Then the second one will be OOV, we call it, that is out of vocabulary. For example, let me explain. For example, you are building a machine learning algorithm, a machine learning model, and there the model has been trained on this particular sentence, for example. So this particular sentence meaning you will have this list. So based on this list, this four words, this list, the model has been trained. Okay, that means the machine learning model input size will be 4. Now in the test data, for example, another sentence comes. That is, I watch Gaurang-Tech YouTube channel and and I listen to his music on Spotify, for example. So now this simple sentence has increased to so many words. Now, how many words we have? We had 5, then 6, 7, 8, 9, 10, 11, 12, 13. 13 words we have. Now, in the test data, you tell me, we be able to incorporate this particular sentence? It will be a no. Why? Because in machine learning models, the input size is constant. So if we specify in the training data that there will be only 4 or 5 input, input tokens, then in the test data also it should be same. So that's where the disadvantage come. That is out of vocabulary. Now we won't be able to test with this new sentence, which have more number of tokens, or you can say more indexes. So that is another disadvantage. Now the third one, sorry. Now the third one will be it do not hold semantic meaning. Again, one hot encoding does not hold any semantic meaning. Yes, it does hold the syntactic meaning, but again, it fails to hold the semantic one. That is, it is able to very nicely represent each word, but it is not able to make any relationship between these corresponding words. That it is not able to make a relationship between what is relationship between watch and Gauranga-Tech or the other words. So that is one. There is another disadvantage of one hot encoding. Now, if we move ahead with bag of words. So, what is bag of words? Bag of words is again another way of vectorization. It treats sentences, or you can see the documents, as collection of words, and it just do not care about the grammar. I'll just explain with an example why I'm saying so. Okay, let's just uh, take this two documents. Take these two documents. The cat document one is the cat sat on the mat, and document two is the dog lay on the rug. Okay, what will be the unique vocabularies out of these two documents? So if I try to find out the unique vocabularies, it will be the cat sat on, the won't come. It has already it came before mat. Then the again won't come. Then dog lay on won't come. The won't come. Then rug. So these are the unique vocabularies we have. Now, in order to do the bag of words representation, what we'll do in the document one, let's see the first word in the vocabulary. That is da. D present D present 2 times. So it will be 2. Then how many times the other word? That is cat is there. Cat appears twice. Sorry, cat appears once only. So again it will be 1. Then set 1 again on once. Then mat once. After that it will be 0 0 0 because uh, dog, lay, and rug are not there in document 1. Again, in document 2. In document 2, the first word, that is D. D comes in once. Sorry, it comes twice. Here and here. So it will be 2. Then cat set. These two words doesn't appear in document 2. Then we move ahead with on. On appears once. Then again, mat is not there. Then again, dog, lay, and rug. They appear once. All three words. So that is how we represent bag of words. Now, if I just move ahead and talk again, sorry, again, so this is one bag of words. So if we talk about binary bag of words, we won't be talking about the frequency. That means in document one and two, you can see the first index. There is two. In binary bag of words, we don't have it. We won't do the counting of how many times a word is occurred, but instead we will just see if that particular word has occurred or not. If it has occurred, irrespective of how many times it did, we'll just place it 1. and if it doesn't occur, it will be 000. For example, if we'll do binary bag of words representation here, then this this will be 1 because this particular word has occurred. Rest will be 0 and rest all will be same. 111 and 000. Then again, for this document too, it will be 1 because this particular word has occurred, has appeared there, and rest will be same because if it's present or not, rest represents there only. So yeah, that is how binary bag of words is represented. If I move ahead with the advantages and disadvantages, again, the advantages will be it's a simple and intuitive, easy to understand, and so on. Disadvantages will be sparsity that I have explained in one hot encoding. The same problem is there. It has a lot of ones and zeros, as you can see. Just to represent a single document, there are so many ones and zeros that takes a lot of memory and RAM, and that increases our computational power. That requires a lot of computational power. Then the second one is again OOV, that is out of vocabulary problem. Again, we have this constant number of test data. For example, the example that I gave before. For example, in the test data, we'll have two more words. For example, we have ndoc. For this document one, if this sentence comes in uh, test data, you see how will you do the bag of word representation, because in bag of word representation there are only this few unique words. How many unique words are there? One, two, three, four, five, six, seven, eight. So the index are in the documents also. You will see the indexes will have, it is total 8 only. One, two, three, four, five, six, seven, 8. Now if this new sentence will come with end of, then it will have more, it will require more indexes to represent it. That is why we cannot incorporate that sentence in this particular representation. So that's one disadvantage. Then again, third one is semantic meaning. As I've already told you in the definition itself, it just do not care about the grammar. It just separates the multiple documents or multiple sentences into one just unique vocabulary list, and then it does the representation, diagonal representation. So it does not hold any semantic meaning. That is another. That is the third disadvantages of bag of word representation. Let's just move ahead with the third topic, that is engrams. So engrams is again one more interesting topic. Engrams is basically contiguous sequences of n items. So contiguous meaning in contact with. I'll explain with the example below what it actually tries to mean. So for example, let's take the example of there is sentence that is I am a data scientist. So there are three verticals in engrams. First one is this unigrams, bigrams, and trigrams. Unigrams means uni means one, bi means two, and tri means three. You must be knowing about it. So if I talk about in unigrams, and then in unigrams, when I do the tokenization, when I separate the tokens of from the sentence, so it will be this list. You can see the list will be I am a data scientist, and every word is one token. And when we do the representation, see how I do. Every token will be the features. There's feature 1, feature 2, feature 3, feature 4, uh, feature 5, all these features, and these are being represented as how we used to do in bag of words, or you can say how we did in one hot encoding. That is based on its indexes. That's, for example, the third word, that is I, the first token. I is present in the zeroth index, so the zeroth index will be 1, and the rest will be 000. And again, how many indexes will be there is based on the list that we get after we do the tokenization. Then for the second word will be 01000 because it is present in the first index. Then for A is present in second index. Then it will be 00100. Sorry. Yeah. Then for data is present in third index. So it will be 00010. And for scientist is present at the end. So it will be 000 and more zero. Sorry. How many zeros will be there? One, two, three, four. Four zeros and one. That is how we represent in unigrams. Okay, I hope you understood this. So now if we talk about bigrams, bigrams means we'll have two words that will be in contact together. That's what contiguous means in the definition that the word that I used. So if we do the tokenization here, a single token will be combination of two words. So how will it do? So how will it work? I'll just show you. If I go to the sentence, if I do a tokenization in bigrams, it will be this will be first token, this will be second token, this will be third token, this will be fourth token. As you can see, the list we get here. Then again, the vector representation will be same. We'll have this different number of features: feature one, feature two, feature three, feature four, and then we'll do the representation. Okay, this is in the zero to index, so it will be one and zero. How many are there? One, two, three, and four. Okay, total indexes are four. So zero. One, two, three, four. Yeah, four. Then for this one, it's present in first index, so it will be this zero, 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 one, zero. Then for data scientists, it's in the third index, so it will be zero, 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 and one. That's how we do the differentiation in diagrams. Okay, let's move ahead with trigrams. In trigrams, as by the name itself, it explains that the combinations will be of three. Okay, let's remove this. Okay, how the tokenization will work in trigrams. So the first token will be this tree, second will be this tree, third will be this tree. So there will be only three tokens. That means how many indexes? Three indexes. So how many features? Three features. Feature one, feature two, feature two. Representation will be 1, 0, 0. This will be 0, 1, 0. This will be 0, 0, 0. And from where I am referring all these things? From this particular list that has been created after the tokenization. So yeah, that explains what engrams is. Now if I just uh, move ahead with its advantages and disadvantages again. If I talk about the advantages, it's very simple and intuitive. It's very easy to understand, as we can already see. Then the second advantage is, see that this was a disadvantage for all other topics for one hot encoding and bag of words, but it holds and grams hold semantic meaning. The reason behind this you can see there are so many different combinations that we are making. So different combinations makes it easy to hold its semantic meaning and not only the syntactic meaning. Then again, the third advantage is the flexibility of n. The n-grams talks about there are three grams as you can see: unigrams, bigrams, trigrams. So it gives us the flexibility. So that's again one advantage. So when it is useful, for example, you have a data and you have a very complex data set, and in order to understand it, this different grams, the flexibility in N helps us to do the processing and whatsoever we want to do with the data. Then again, the disadvantage remains same for most of this word embeddings techniques, that is sparsity. Then again, you can see there are so many ones and zeros in here to represent this only just to represent this three feature in the trigrams. You will see there are so many ones and zeros, so that creates a lot of memory, and it requires a lot of computation power as well. And let's just go ahead with our last topic, that is TF-IDF, term frequency and inverse document frequency. Okay, what it says. It says that TF-IDF is a measure used to evaluate the importance of a word in a document relative to corpus of data. So we have two separate formulas to find TF and IDF. TF is number of times word appears in a document, that is in a sentence, divided by total number of words in the document. And IDF is the log of total number of documents divided by number of documents containing the word. I'll explain with an example uh, so that we are able to understand it properly. Okay, let's just take these two documents. The cat sat on the mat and the dog lay on the rug. So if I try to find the TF-IDF for the word cat, it will be uh, for the TF will be uh, in the numerator it will be number of times word appears in a document. It will be one. Definitely in document one, how many times cat has appeared? It has appeared only one. And the denominator will be total number of words in the document. So in document one, how many words are there? One, two, three, four, five, six. So it will be 1 by 6. That is TF. Now IDF. IDF. For IDF, it will be log of total number of documents. We have two documents, document 1 and 2, divided by number of documents containing the word. So it is 1. We have only document 1 that contains the word cat. It will be log of 2, which is approximately 0.302. Now, if we just do the multiplication of TF and IDF, TF multiply ID, IDF, we get 1 by 6 multiply 0.302. It results in approximately something approximately 0.05. Sorry, I'll write it once again. It is approximately 0.05. So yeah, that is how we calculate TF-IDF. Okay. Now, if I just talk about the advantages and disadvantages of TF-IDF, so advantages will be it is simple, so it has a specified formula. We can just use it and find the TF-IDF for all the tokens or all the words that we have in both the documents, and then we will have the vector representation. And the second advantage is basically it is highly this particular concept of TF-IDF is highly useful for search engines. For example, if someone is trying to find a document based on a query, that's when we can use TF-IDF in search engines. And if I talk about the disadvantage is again, this lacks the semantic meaning. TF-IDF do not hold the semantic meaning. But again, one more advantage is uh, it gives for other embedding techniques. We saw that if a particular word is present in a document or not, it just tells us that based on its representation. So if it's there, it just gives one, and if it is not present, it just gives zero. In other one-hot encoding or bag of words, we have seen that. But in TF-IDF, it gives weightage to the words that has more relevance. As in the TF-IDF score will be more in comparison to the other words whose weightage will be less. For example, if a particular word is occurring twice or thrice in multiple documents, so that particular word, for example, this particular word da here, this is occurring twice, this particular word da. So this particular word will have more weightage in comparison to a particular word dog that is appearing just one in one document. So that's again one advantage of TF-IDF. So yeah, that is all from my side. Hope I could explain all these topics.